start the recording. Yep, I hope you can see and hear me. Okay, yeah. So today we'll look at the concepts that were introduced and discussed in week 11's lecture series. So I'll just briefly go through the concepts that you would use to solve this week's problems. And yeah, we'll also solve questions from last year's assignments as well. And yeah. So in the week 10, we had seen about how you decide whether an estimate is good. So there were several characteristics that an estimate should satisfy to for us to call it a good estimator. So in week 10, we saw about uh, un we saw about the unbiasedness. So an estimate has to be unbiased. And we also saw about the efficiency of an estimator. So yeah, in this week, the first part of the week was about consistency and sufficiency of estimators. So previously we have seen about the convergence of probability. So we had seen that the difference between the actual value and the estimated value. So the difference should be less than a given value epsilon, not a given value. This should be smaller than a certain value. So the probability of this difference being less than epsilon should tend to 1, and it tends to 1. And as n tends to infinity, this probability also approaches 1. So it just means that when you have a higher sample size, it's more likely that the probability of this difference is very, very high. And the probability that this difference is higher would be 0. So yeah, this applies to any estimate. So here we saw that theta hat was our estimate for a parameter theta, and the same could be applied here. So the probability of the difference between theta hat and theta has to be less than epsilon, and this probability has to be closer to 1, and when n tends to infinity. Yeah, so here's just an example of a normal distribution where you have a random number that follows a normal distribution with mu mean and standard deviation of sigma square. And when you have a new random variable, which is the average of a given set of random variables, here your this random variable will follow a normal distribution with mean mu and sigma square by n, which is your sample size. So here the variance of you can see the variance here. So as n tends to infinity, so when this value of n increases, your variance will decrease. So a good estimate is where your variance is close to 0. So yeah, as n increases, the variance decreases and it tends to 0. So that's what we mean by weakly consistent and MSE consistent. So there's one more thing, the mean square error. Your MSE should also tend to 0 and your variance should also tend to 0. So if your random variable the variance of your if your random variable satisfies these, it means that they are consistent. So the next property of a point, so all of these that we're discussing, these are about point estimates. So the next property is sufficiency. So here we can just see that, so sufficiency is basically to judge the quality of an estimator. It's to it's for us to know whether an estimator actually tells us something about the value. So here you can see x is a random variable with normal distribution mu comma sigma. So it has a parameter mu, and y is also another random variable with mu and sigma, which is 1. So both of these estimates, they tell us about mu. So yeah, this is sufficient. This is enough for us to derive mu, the actual value of mu, like an estimate of the actual value. So this is what you call sufficiency. Mm. Yeah, so it was just given by two examples. You have two estimates. So you are trying to estimate the actual value of mu. So you have an estimate mu1 hat. So this has a mean of 2 mu, and your mu2 hat has a mean of 0. So this 0, with this 0, this tells us nothing. There's no way we can estimate your actual mu. But with 2 mu, this is a good estimate. It tells us something about your mean. So this is a sufficient estimate. Whereas this one is incomplete, like it's missing information. So it actually loses information. It loses information about mu. Mm, yeah. And here we could see another example where like one estimate mu1 hat. No, sorry. I think I have hidden the slide. So yeah, let's say one estimate is mu and mu2 hat is something like mu by 2. So in both these cases, we have this parameter mu. So here, both of these are sufficient. So it has some information about mu. So this is, so there's also a way to derive whether, like to mathematically tell us. So there's a way to mathematically tell whether an estimate is sufficient or not. So that is called Neyman-Fisher factorization. So what this basically means is that, so we have random variables, we have random samples x1 to xn, and they all follow a probability density function or a probability mass function f of x. So this could follow anything. It could be a normal distribution, Poisson. It could be like uniform distribution, Bernoulli. It could be any distribution. So we also have a statistic. Statistic is basically any operation on these random variables. We have these. And so this statistic is said to be sufficient for the estimate. So let's say we are trying to estimate a parameter theta. So the statistic is sufficient to estimate theta, and only if the joint density can be factorized. So let's say you have a number 15. So this can be broken down into 5 and 3. So, so 5 multiplied by 3 gives you 15. So in the same way, you try to break down your actual this f of x of all of your random variables, the whole sample. You break down to the probability function and something called h of x to n. So you're splitting the actual distribution function into two terms, term 1 multiplied by term 2. So one term, this term has the estimate, and the second term, it does not have any estimate. It doesn't have any unknown value. It only has all these known values of x. It has xi. Whereas this one has your actual value. So yeah, let's look at examples to understand this. So this can also be written like for theta, like theta 1, theta 2. So x1, x2, xn could also be like theta 1, theta 2, theta n. You can break down the equation like this. And we see an example of normal distribution here. So normal distribution, you know your, so here it's given, it follows a normal distribution with mean mu and sigma square 1. So the actual f of x for a normal distribution is 1 by sigma uh, root 2 pi exponent of 1 by 2 x minus mu by sigma square. Exponent of minus 1 by 2, this minus here. So this is your equation for f of x of a normal of a random variable that follows a normal distribution. So now you have many such random variables, x1, x2 until xn. So now what you do is you just have to multiply. You have to take a product of all of these. So product of these would be, so it would basically be n times. So one here, this sigma is 1, sigma square is also 1. So let's just ignore the sigma term here. So it becomes 1 by 2 pi e power minus 1 by 2 x minus mu square. So when you have n terms, let's just break this down into this part. So when you multiply 1 by root 2 pi n times, it just becomes 1 by root 2 pi to the power n, which is given by this. And also the exponent, you can split it into two parts because let's just break it down. So e power में you have 1 by 2 summation of xi minus mu the whole square. So you can split it as, like, let this minus just be outside. You can have xi by 2 the whole square. Am I making a mistake? No, let's just keep 1 by 2 also outside. It's just a constant. Let's just break down this part. A minus, it's in the format a minus b the whole square. So you have a square plus b square minus 2ab. You can see that here. And yeah, so they've basically taken this part and sorry, they've taken, I make, yeah, so they've taken this part separately, which is your second term here, which is your hx term. It doesn't have any mu. It doesn't have your estimate. It only has the statistic. It has the summation of your xi. So this is this. And this part is goes here. So yeah, like you can see, you can break down this a probability function into two parts. One that is of the form h of x1, x2, xn, which tells us nothing about the estimate, and the other part which is g of t comma mu. It has the mu term. It has the estimate. So it can be broken down this. So it here this is the statistic. Like the statistic is summation of xi, and this is sufficient for us. So this is a sufficient estimator of mu. So that's what everything explains. This is just one example with normal distribution. So now we saw about the properties of estimators, and and there's two more things called method of moments and maximum likelihood. So let's discuss each of these. So yeah, we have seen, like, probably in the first 2 weeks of your course about something called moments. So this is called the rth moment about of x about a point A. So the rth moment around A, where like around the origin when A is equal to 0, is called the raw moment. And this is how it's just given by. You can just there's nothing new about this. And this is called a central moment and mu r. So when mu is calculated, when A could be like 1, 2, 3 or anything. So it's the rth central moment of x. So even here, it follows the same convergence property. So as the difference between the moment, oh, sorry, what's mu? I think I just missed something. Yeah. Yeah. So the mean, so your method of moment that you calculate is given by m around the rth moment. So that should tend to your actual mean, your estimate. Sorry, your actual parameter. So the difference between these should, the probability of the difference between these has to be high. It's the same as convergence property. So here you have the unknown parameters, which is your population parameters, and you have your sample parameters.
Ma'am, can you explain that, ma'am?
Yeah.
Can you explain that again, that moments and mu are the difference?
Okay, so yeah, I was just trying to explain, but yeah, I missed it. So
Yeah.
say we have a population and we have a sample. Mm. So when your no, let's say, how do I explain this? Uh, Okay, let's just consider A is equal to 0. And when A is equal to 0, your expectation of g of x will be e of x, which is your mean. Okay, so this is your raw moment. So now we have a sample-based raw moment. So using the sample parameters, we calculate this moment, and this is called MR, M prime R. And so with this, you have to estimate your actual population's moment. That is given by mu R prime. So this is MR mu R, sample population. So the goal of all these estimators is to estimate the actual population parameter using a sample parameter. So earlier we saw theta hat, and it has to tend to theta. And the probability of difference between theta hat minus theta has to be 1, like close to 1. So similarly, in the case of moments, your sample moment has to be close to your population moment. And this difference, MR minus mu R, this has to be close to 1. So that's what is given in this slide. Was that clearer?
Yes, ma'am. Understood. Understood. Thank you, ma'am.
So yeah, so these equations, these are so moment is actually it's a formula. It's not your actual parameter. What I mean by moment is not your actual parameter of mu, but you have a certain formula, like a derivation. Like you'll have 2 mu is equal to something. So using this actual term, you can solve this to get the actual value of your unknown parameter. Uh, Let's look at some examples. Okay. So here we have a random sample, x1, x2, xn. So this forms an exponential distribution with a parameter lambda. So lambda is our unknown here. So yeah, we have the sample moment. So here it's basically E of x. So expectation of x, like your x is basically x1, x2, x3. So expectation of your x is basically an average here. So average of this is given by x bar. And we know from exponential distribution, we already know, like in previous lectures, we have seen that expectation of x for an exponential distribution is 1 by lambda. So here what happens? 1 by lambda is equal to x bar. So with this equation, you can estimate lambda, which is your unknown. X bar is known. X bar you can calculate from your x1, x2, x3. So now how do you calculate lambda? So 1 by lambda is equal to x. So lambda is equal to 1 by x bar, 1 by x bar. So this is this is an example in case of exponential distribution. So here they're given an example here. They're given different values for x, x1, x2, x3. So if you want to calculate lambda for all of this whole population, what do? This whole sample, you do 1 by mean of x. So with R, you can try this out. You'll get the value of this lambda method of moment estimate. So the next example is in case of Bernoulli distribution. So here we know it follows some f of x, p of x, 1 minus p, 1 minus x. So yeah, we don't need this here, but here expectation of x, again so x is always x1, x2, x3. So expectation of x would be x bar, an average of this. So for Bernoulli distribution, the expectation of x is equal to p. So p is equal to x bar. So this is just straightforward. So if you calculate the probability, if you find this value of the probability, so that is equal to x bar. So sorry. So p here is the unknown. This is what you need to estimate. So if you just calculate x bar from this, that gives you the value of p. So here, next one, we have a uniform distribution. So again, already we have E of this x is equal to x bar. So the expectation for a uniform distribution is given by lambda by 2. So lambda by 2 is equal to x bar. It's not lambda, sorry, what is this? This is theta. So theta by 2 is equal to x bar. So theta will be equal to 2x bar. So this is how you estimate this unknown theta. And same way, we have normal distribution. So normal distribution E of x is equal to mu. So mu is equal to this. So here we calculate the moment around, if A is equal to 2, what happens is you have your E of x square is equal to mu square plus sigma square. Mu and this is x, no, x bar. So in the first case, like if A is equal to 1, your M1 prime, you will have E of you'll have x bar is equal to mu. If A is equal to 2, M2 prime, so you basically need to solve for this. So if you have, so here what they're doing is they're considering this as one value. This is xi. So mu square plus sigma square is xi square. So when you take an average of this, what do you get? You have to just divide it by n. Like summation of this xi divided by n. So that's what it's given here, xi square. Yeah. Mm, okay, and then there's a similar way to estimate your unknown is just a second. Okay, another way to estimate is using maximum likelihood estimation. So what this means is that you have multiple random variables and you just take a product of the function, the probability function of all of these. So that's given by this. So this capital Pi means a product of the f of x, xi given theta. So this product gives you the likelihood estimate of theta. So likelihood function is a function of theta, is function of theta given the observed and known sample values. So, wait, what was I saying? So the product of all of these probability functions gives you a likelihood estimate. So this is a function of theta, which is calculated, which is derived using your sample parameters x1, x2, x3, and your known, your observations, which is like theta hat, the estimates. Yeah, to be more like to explain what exactly this tells you. Uh, let's say you have a curve. So you need to find the maxima or the minima of it. You need to find the this estimate. So the slope at these points would be 0. So that's why you have a probability function f of x. To find the maximum likelihood, you do a differentiation. So like differentiation of your f of x, it gives you this slope. But this 0 would mean that your your estimate, your parameter could be either here or it could be here. Sorry, not this. Your maxima, like this part. It could be either here or it could be here. So when you double differentiate this, you'll get some value. So that value will have a positive or a negative sign. So positive sign means it's at this point, and a negative sign would mean that it is here. So this is just an overview of the concept. So this gives you the maximum likelihood estimate. And let's just look further about this. It's easier to explain. Yeah, we will look at problems that use this concept. So you'll understand better when we discuss it there. Uh, yeah, so just for now, let me just explain this. So we have this random sample that follows a uniform distribution, mean and theta. So this theta is our parameter, which is unknown. It follows a PDF. F of x is equal to 1 by theta for 0 to theta. So this value we need to estimate. So f of x is we have f of x. So x1 would have 1 by theta 1. x2 would have 1 by theta 2, and so on. Like it'll have different values. So you have to take a product of all these. So if you take a product of all these, what will you get? You'll have 1 by theta into 1 by theta into 1 by theta into like whatever the number of n is. So this will be equal to 1 by theta power n. So this is your likelihood estimate. So the maximum likelihood estimator of theta uh, so this 1 by theta power n is your maximum likelihood estimate of theta. So this means that if theta is small, this value will be high. And if this value is low, your theta will be, it's just like inversely proportional. Yeah, we'll look at more problems when we solve it. Okay, the next part was about confidence intervals. So we saw about properties of estimators and some methods to derive your estimate, derive your unknown parameter. And the next one was confidence. So confidence interval is basically like we have seen curves like this. And let's say we have a parameter, population parameter mu. So mu lies here. But we don't know where exactly this mu lies. So what we do is we have an interval. We estimate an interval. So far we just learned about point estimates. But here it's an interval estimate. So it just tells us that within this interval, you have high probability that you will find your actual parameter. So you must have heard something like 95% confidence interval. 95% confidence interval. So that means that 1 minus alpha is equal to 0.95. So this part is 0.95. So 95%, there is like 95% probability that your estimate will lie within this interval. And the rest of this is alpha by 2, alpha by 2. So let's see how we can calculate this uh, interval. So so what is explained here is that it is more ideal if your interval is small. So if your interval is small, your estimate of mu will be precise. So this will actually maximize the probability of mu hat minus mu. But if your interval is large, it's more uncertain. Your estimate would also lie here. So the difference between your actual value and your estimated value would be higher. So it is more preferred, like it's more ideal if you have your estimate, the interval of your estimate should be small. So when we calculate the interval, what do you have? You have an upper bound and a lower bound. So that is given by theta hat L and theta hat U, their lower limit and upper limit. And your theta lies within these two values. And yeah, so this whole area, this theta L to theta upper will have an area of 1 minus alpha. Did somebody say something? Okay, let's go ahead. Okay, yeah, no worries. So this is a general way to derive a confidence interval. So you have this g of x is given by like this formula. So this parameter, this value here, it depends on both the sample and your actual parameter. But the probability distribution of this function is just follows a normal distribution, and this does not depend on your theta or your actual parameter or any other unknown parameter. So yeah, let's just look further. We'll look at problems of how we can calculate this. So there could be many instances. So you have mean and sigma square. Sometimes your mean would be known or it could be unknown. And similarly, your sigma square can be known or unknown. Sometimes you might not be directly given the value. So when I say known, either you'll be having your population mu or you'll be having your sample mu. And using this, you can estimate your mu. And similarly, you can have your sample standard deviation, and with that, you can estimate your population standard deviation, sigma square. So these are several instances. And yeah, let's look at the equations for each of these. So the first case, no, this is just the generalized term. Let's look more specific. So let's say we have a two-sided confidence interval. Two-sided interval means like you have something like this. Here, your variance is known. You know your sigma square. So that you denote by this sigma naught, which is your known value. But your mu is unknown. But you can derive mu using x bar, your sample average, your sample mean. So yeah, you just need to apply this formula. So you'll get your lower limit and upper limit if you apply x bar minus z alpha by 2 sigma by root n. N is your sample size. So this could be plus or minus. So this is a symmetrical curve. So your lower limit, to get your lower limit, you use minus. To get your upper limit, you use plus. So you just have to substitute these values and you'll get it. So you need to remember this. Sample interval, CI for mean, known variance. Variance is known. So what does this mean? You're estimating mu using x square, x bar, sorry. You are estimating mu from x bar with sigma square known. Yeah, I'm sorry. I just don't feel very well, so just bear with me. Yeah, I sound weird. Okay. This is just some example. We'll skip this slide. Yeah, we also covered this. So yeah, this is basically what you're estimating. You substitute this formula, you'll get this point, and you substitute x bar plus z alpha by 2 sigma by root n, you get this point. So the next, this is again the same thing. They're just showing you how you can calculate it with R. But yeah, we can go through these slides. What is this? Yeah, again, so the previous example we saw was two-sided confidence interval. So in some cases, you will have the same, you'll need to estimate mu using x bar, known variance, but you just need one-sided estimate. So what does this mean? It could be either one-sided upper or one-sided lower? What does one-sided upper mean? Upper means that you'll have this infinity and you have to calculate this point here. Your one-sided lower CI, one-sided lower CI means your interval tends between minus infinity to a certain point. So this you have to calculate. Yeah, so in case of lower, you just need, oh, sorry, in case of upper, you need to apply this formula, and lower, you need to apply this. Right. To make it easier, just write x minus. Okay, now one more thing is you have a term called an error term. So this is basically your error term. This value here.
Ma'am, what is the formula for one-sided upper confidence level and confidence interval?
Upper. Yeah, this is the formula.
Okay.
Yeah. So this is in case where you estimate mean with known variance. Yeah, similarly, we'll see for other cases. We'll look at a problem also.
Ma'am, can you define the level of significance, ma'am?
What does that mean? Level of significance?
That is alpha. That is alpha.
Oh, so alpha
Alpha.
is basically your area of interest.
That is probability of type 1 error occur. That's a definition. So in our prediction, we are setting that 5% error is going to come, or 1% error. Is it, what is that? I don't understand clearly. We are predicting 95% confident means 95% it is true, or what comes to say this prediction?
95%? Yeah, so your value lies within this 95% confidence interval. So that's what this means.
Here you have written the 100 into 1 minus alpha percentage, one side lower confidence interval for mu is written. What is the meaning for the 100 into 1 minus alpha percentage?
So if you're so let's say when we say 95% confidence interval, so this is basically your 100 into 0.95%, which is equal to your 95% confidence interval.
Okay, that is understood, ma'am. That is
100
understood.
into 0.95 is 95, yeah. This could be anything. So that's why they've just denoted it this way. It could also be 75. This 1 minus alpha, it can be 75, like 0.75. In that case, it's a 75% one-sided confidence interval or whatever it is.
Before our prediction, we setting that there is a error that is 0.5 or 0.1 percentage in our
We're
calculation.
not talking about error here. It's just we are estimating an interval. So we are not able to do a point estimate here. In that case, we are just saying, oh, the mean value lies between 20 to 22. It lies somewhere. It could be any point between that. So we're just defining it as an interval.
So what that alpha denotes?
Alpha is just your area. So if you remember this curve, we know like the end of the curve, it was alpha. So your area of interest is the remaining part. So this is just 1 minus alpha.
Accepted region, rejected region.
Yes, area of
Okay.
your interest, basically.
Okay, that is region. Okay. Okay. That accepted region we define like that. By using the formula, confidence interval formula, away the apart from that interval, that is a rejected region. Am I right?
Mm-hmm. Yeah.
Okay. The formula. Okay.
So if you're like if you're trying to estimate mean, you want it to be close to this part. You don't want your mean to lie somewhere here. You don't want your estimate to be here. So it's ideal that your estimate lies somewhere around this region.
Okay, we cannot find the estimation 100 percentage. We can
Yeah.
find around 19 percentage confident only. Am I right?
Um, that's not how you say it. Okay, wait. So basically you're just asking like how do you define like what do you mean when you say 95% confidence interval? So it's just like 95% of the time that you estimate your value lies between this interval.
Oh, 95 percentage of times that values lies in that interval. Okay, okay.
Mm.
95 percentage true.
Yes, yes.
Is it 95 percentage true or 95 percentage times it may lie? What it is that
No,
predicted
it's
value?
95% it's true. It's more likely that it lies there.
Oh, 95 percentage it is true.
Yes.
So we are not finding
You're
100 percentage.
95% confident that it lies there. It doesn't mean that 95 times you estimate, like 100 times you're estimating. It doesn't mean like 95 values you get the true value and 5 times you get the wrong value. That's not what it means.
Confident.
Yeah, you're just like 95% sure that the value you estimate is between this region. That's why you call it confidence interval.
So one-sided means what is the difference between one-sided and two-sided?
Just a second. Mm. Where was I? Confidence. Just lost it. Okay. Add a slide. Once I let me just use some example. Sorry. So this one-sided, two-sided, it just depends on what you want to calculate. Um,
It depends upon the problem, the
yeah,
setting hypothesis.
yeah, it's just about your problem setting. So let's say I just want to calculate the average age of students in a class. So this average age, it always has to be between two numbers. It can't be between like some number to infinity. Like you can't define it that way, right? But in some cases, let's say you just want to calculate the volume needed to fill up a tank. You just need to estimate volume here. So that in that case, your volume can start from a value. It needs some minimum value. So if it's a 10-liter tank, let's say one, how do I put this? Mm, just trying to. Yeah, let's just get back to this when I see some problems. It'd be easier for me to explain as well. Yeah, I think we'll be there quick. Yeah, I'll just,
Okay, ma'am.
yeah. So,
Here alpha by 2 came, no? Alpha by 2.
yes. So here you'll have alpha by 2 and alpha by 2. But here you just have 1 minus alpha and alpha in like one-sided.
Okay.
Here your region of interest is in a two-sided distribution, two-sided tail. Your area of interest is 1 minus alpha. And the area that you're not interested is alpha. But that alpha is on both sides. So you write it alpha by 2 and alpha by 2. Okay.
Okay. Thank you.
Yeah, we were talking about error. So what do we mean by error? Like, let's just get back to the diagram. This is your actual value, x. Let's say it's x. But you estimate x bar. That is this value here. It's x bar minus z alpha by 2 sigma by n. And this is x. So this is basically your error term. This is called your error term. So this x bar is only close to your x. It is not exactly x. If x bar is equal to x, this term will become 0. Right? This whole term will become 0. So yeah, because it is not the same and there is some difference between x bar and x, that difference is given by this error term. And this is the formula. And from this, you can calculate n. N is the minimum number of samples that you need uh, to get a good estimate of your population. So yeah, these are just some equations, formula you might need to remember. And yeah, so far we saw the case where you're estimating mu and variance was known. And now let's see, we estimate mean, but variance is unknown. What do I mean when I say this? So as usual, we use x bar to estimate mu. And here sigma square is unknown, but we might have sample standard deviation. So using this, you estimate this as well. And we have Ci for mu, unknown variance. So in that case, you use this formula, two-sided. Here, instead of Z, which is a normal distribution, you just use a T distribution. And S is your sample standard deviation. N is your sample size. X bar is your average of your random variables. Remember this. And even in this case, you have this one-sided upper, one-sided lower. So what do we mean here again? We have some infinity. Here we are interested in this value. This is your area of interest, and this is alpha. So this point is given by x minus t of a, comma n minus 1, your degrees of freedom, s by root n. This is upper Ci. Similarly, lower Ci, minus infinity to t alpha n minus 1 degrees of freedom, s by root n, sorry, x bar plus. And the same way, you have an error term here, and you calculate n from that. And what is this? This is not the same thing. So here, we know that for a sample size, if n is greater than 30, your t distribution will become a normal distribution. So yeah, when you have a large sample size, for same, you estimate mu with unknown variance, you use this formula. Instead of t distribution, you use a normal distribution if you have more than 30 samples. So far, we estimated mu, right? But now we are estimating the sigma square. We are estimating the variance. So we are calling it confidence interval for the variance of a normal distribution. So even in this case, you have your sample mean and your sample standard deviation. And so here, this follows a chi-square distribution. Fine. So chi-square distribution is not symmetric. It's asymmetric. So it looks something like this. It's skewed. And yeah, you have alpha by 2. And this value, you can't write like x plus or minus z alpha by 2. You can't write it like that because it's not symmetrical. So instead, you'll have something like this. Chi-square 1 minus alpha by 2. And here you'll have chi-square alpha by 2. So this case is for confidence interval for mu. Here mean is also unknown. This means your x bar is unknown. You're estimating mu, but your x bar is unknown. But you have your sample standard deviation. So in that case, you use this, your confidence interval. So I think this is wrong. This is, yeah, sorry. Confidence interval for sigma square. Confidence interval for the variance. So you have your sample standard deviation, and with that you calculate this. Yeah, so these are the major formula you just need to remember. Yeah, let's look at problems now. What's the time? Yeah, we still have an hour. That's good. Okay. Okay, now. So let x1, x2 to xn be a random sample from a population with a normal distribution, mean and variance. Assume sigma square is known. Let x bar is equal to 1 by n. Yeah, they're just defining all this. So if x bar is equal to 1 by n, this, then your variance of wait, let's just come back to this. So this is what we have. So let's say we have three estimators, mu1 hat, x bar. We have mu2 hat is equal to x bar by root n. Mu3 hat is equal to x bar by n square. We have these three estimates, and we need to find which are consistent. Comment about the consistency of the estimate. So how do you know if an estimate is consistent? So we just saw that we could calculate the variance of your estimate. So this, your variance has to tend to 0. Also, your MSC has to tend to 0. If it satisfies either of these two, your estimate is said to be consistent. So here, variance is known, right? So variance of x is sigma square, but we have x bar. So x bar is the summation of x. So variance of x bar is equal to, so yeah, remember this. Let's say we have variance of NA. So this will become n square variance of A, right? So with that logic, what happens is we have n into sigma square divided by n square. So 1 by n, it comes out, it becomes 1 by n square. This n is because we are multiplying multiple standard deviation. Sigma square into sigma square into sigma square up to like n. So that's why you're writing n sigma square. This while coming out n square. So you cancel these. So variance of x bar is equal to sigma square by n. So this is your first estimate. So variance of mu1 hat is equal to variance of x bar is equal to sigma square by n. And now let's go to the second one. Variance of mu2 hat is equal to variance of x bar divided by root n. We already know that variance of x bar is equal to sigma square by n. Now we have this extra term 1 by root n. So when you bring this 1 by root n outside, what happens? It becomes 1 by root n square. So 1 by root n square is just 1 by n, right? Like root n into root n is equal to n. So this in the denominator, you will just have sigma square by n into 1 by n. So you have sigma square by n square. So variance of mu1 hat is equal to sigma square by n, the first one. Second one, we just calculated variance of mu2 hat is equal to sigma square by n square. Now your third estimate, variance of mu3 hat is equal to variance of x bar, which is sigma square by n, divided by n square. So n square, when you bring it out, it becomes n power 4. So you'll have sigma square by n power 5. So your variance mu3 hat is equal to sigma square by n power 5. So in all these three cases, you have n in your denominator. So as n tends to infinity, so variance of all these three estimates will also tend to 0. So all of these are consistent. All are consistent. So yep, that answers this question. So next problem. It's a similar.
Excuse me, ma'am.
Yeah.
Ma'am, in the last question, variance or MSC, any one of them needs to be 0, or both
Yeah.
of them needs to
Yeah.
be 0.
So either one. Either one can be 0. But
And
here,
the expectation, yes, ma'am.
yeah, here because variance is known, we are just calculating variance.
That's yes,
That's
ma'am.
enough.
That's the dot because MSC can't be 0 in case of a biased estimator.
Yes, yeah.
Ma'am, compare with variance of mu1, variance of mu3 will tends to 0 soon.
Yeah, soon. But that's not the question. The given options were only, it was just like mu1 is consistent, mu2, mu3 are not consistent. So yeah, among all the options, all are consistent. So the question is not which is more consistent. They just asked whether each of these are consistent or not.
Okay, understood.
Yes.
And ma'am, the expectation of the estimator should be equal to that of the sample.
Mm, I don't get it.
Like if the expectation of the estimator is not equal to that of sample, then can we directly say that it is inconsistent? Like for example, in this question only,
Mhm.
over here the x bar is given as 1 by n summation I equal to 1 to n xi. So its expectation would be mu,
Yes.
and let's take an estimator mu2 hat, which is given as x bar divided by root n.
Mm-hmm.
So its expectation would be 1 by root n mu.
1 by root n. Mm-hmm.
So can we directly say
Not
that?
clear, because this itself is an estimate, right? It's not your actual mu. So that's why you're basically just estimating this. Like mu1 hat.
Can you please repeat, ma'am?
Mm. Yeah, I'm not sure if I understood it right. So the goal is to reduce your difference between mu hat and mu. So this difference is actually your variance. Reducing this means it has to tend to 0. It cannot be exactly 0, but it has to tend to 0. It has to be closer to 0. That's what we're trying to do.
So why we have to check for MSE then? Because MSE doesn't have any biasness term in case of an unbiased
Yes, that's
estimator.
why we're not looking at MSE here. So we don't know about the bias. We don't know about anything about that. So here we only know about the variance and we are using that.
So basically, we have to check for variance of the
Yeah,
estimator.
we just have to check for variance.
Okay, ma'am. Thank you, ma'am.
So your other term is also, sorry, the next question is also similar. You have x1, x2 until xn. So let this be a random sample with a population with exponential distribution whose PDF is given by this f of x is equal to 1 by theta e power minus x by theta. So there are two estimators here. Theta 1 hat is equal to x bar and theta 2 hat is equal to x bar by n power 3 by 2. So here, you know that expectation of x is equal to theta for exponential distribution. So variance is given by, variance of x is given by theta square. So in the same way, so if theta 1 hat is equal to x bar, then variance of your theta 1 hat would be variance of x bar, just theta square by n. Now in this case, you will have theta 2 hat is equal to variance of x bar by n power 3 by 2. So you'll have theta square by n power 3 by 2 square. So yeah, even in both these cases, as n tends to infinity, your variance will tend to 0. So even here, both are consistent. Because n is in your denominator, both are consistent. So when you calculate this, if you end up with a term with like n theta square, so this will not be consistent. This is not consistent. So as long as you have n in your denominator, you can say that as n is increasing, variance also decreases. So yeah, so both of these are consistent. Now,
What is n theta square? I don't understand. N
it's
power 3 by 2 the cancelled 2 n cube only coming.
okay, whatever that is. So you have n power 3 by 2. When you bring this out, you have to take a square of this. That's why I written it this way.
N cube. Theta square by n cube only. How it is n into theta square?
I didn't write n into. Oh no, this was just a different example. I was just
Oh,
saying here in all of these questions that we discussed, we have n in your denominator. So even here you
okay.
have n in your denominator. So if that's the case,
So
you can say it is consistent. But let's say
okay.
you calculate something and you get something like this, n in your numerator, then it is not consistent.
Now both are
Yeah, both are consistent.
consistent. Okay.
Okay, next question. Let x1, x2, x3 be a random sample from a uniform distribution with these parameters θ1 and θ2, and f of x is given by this. So which of the following statements is true for sufficient estimators? So sufficient estimators, we saw that we need to have as much information as possible. Like we saw normal distribution mu comma sigma, normal distribution 2 mu comma sigma, normal distribution 0 comma sigma. So in that case, these two are sufficient. And if you have like something like x plus y and you have like mu plus mu, you need both of these terms. So so these are jointly sufficient to estimate your value. So when you have such two unknowns, like two parameters, you need both of them. Both of them are jointly sufficient. So this is just like a theoretical question. So here your answer would be option D. So yeah, these are jointly sufficient for both. Okay. Mm, okay, so this also talks about sufficiency of an estimator. So we just have different distributions. So here we have a normal distribution. So we have the random sample x1 to xn, and mean is equal to 0, variance is equal to sigma square. So we need to say what is a sufficient estimator of sigma square. So we have normal distribution 0 comma sigma square. So if you apply that, you'll have 1 by sigma root 2 pi exponent of minus 1 by 2 x minus mu by sigma square, right? Mu is 0. So yeah, you just have x by sigma square. So when you take a summation, so this is just one for one random variable. So for all of these random variables, you'll basically have to multiply all of these. So you'll have this power n, and you'll have exponent of minus 1 by 2 sigma square. It comes to the, let's just bring it out. And you will have summation of xi square. Because this is 0, you'll just have summation of xi square. So here, if you remember, you can partition this whole equation into two parts. One part which has your estimate, your parameter, sigma, and the other part which is just the statistic, which is your h of x1, x2 until xn. So this part is sufficient estimator of sigma square. So just I is equal to 1 to n xi square is the sufficient estimator. So this is your answer. Okay. Now, similarly, we have Bernoulli probability mass function. So here they've just written, like, instead of p, they've written theta. So if you remember, Bernoulli is given by p power x, 1 minus p power 1 minus x. So here you just replace it with theta, theta x, 1 minus theta, 1 minus x. So this is for one random variable. So for all of these, you just have to multiply them all. You multiply all these. So what happens? You will have so when you multiply the power, what happens? It gets added up. So when you multiply like theta power x1, theta, no, sorry. Yeah, when you have theta power x1,
Function.
so it just into
Are you
theta.
finding maximum likelihood function?
No, this is just sufficiency. We're just calculating sufficiency now.
So how we
Because
are multiplying the fourth one, 4x 1 by sigma 2 square root of 2 power n, square root of 2n whole power n expectation. N times how it is.
Can you go slow? Yeah. What is it? Hello?
1 minute. Yes, ma'am.
Yeah, what was the question?
Yeah, doubt. The fourth problem,
Yeah.
that the second line x equal to second line x equal to 1 by sigma square root of 2n whole power n. How
Yeah.
it is coming whole n?
And that's just like, let's say you have, so let's just say you have 2 power 4. What does this mean? It just means 2 into 2 into 2 into 2. You have 2 4 times. So here n is equal to 4. So 2 power n, 2 power 4. Same concept here. You'll just have 1 by 2n
So
into,
n
you'll just have this n number of times. So you just write this power n. Yeah, you use this example and think about it. 2 into 2 into 2, n number of times is 2 power n. Same thing here. Is that okay?
next step, that is okay. That line is okay. Third line
What third line? This?
gives that line.
No,
How it is coming?
so if you remember, so we first for telling whether an estimate is sufficient, we had something called Neyman Fisher factorization. So in factorization, what did we do? We just broke down this whole equation into two parts. One part is the part that has your estimate, and one part that is just the statistic. It's just your T of x1, x2, etc. It does not have any unknown parameter. It's just some operation on x. So here the operation is a summation. So that is your sufficient estimator here. So I'm just saying this is the answer here. Because the question is the sufficient estimator of sigma square is. So wherever you see such operation, that is your sufficient estimator. And let me go to the slide. Fisher. Yep. Properties of point estimate: sufficiency, factorization. You see it's split into two parts. And this h is a non-negative function. So this is the sufficient. So any one-to-one function of a sufficient statistic is sufficient. See here. That's what we're just deriving. So if you remember this normal distribution, here we saw the summation of xi. So here the statistic t is equal to the summation of xi. So this is your sufficient estimator. It's just the same concept.
Okay, we estimated that our estimator separately g of t comma.
Yes, yes. So this part is your g of t comma your sigma.
Sigma.
Yeah.
Okay.
And this is your h of x1, x2, x3. It does not have any unknown parameter. It's just x.
But there is a exponential of minus 1 by 2 sigma square is there, no, ma'am?
Yeah, you can still split that, right? So when you have exponent of minus 1 by 2 x square by sigma square. So basically you can write this as exponential of, so this is just in the power 1 by 2 x square by sigma square. You can write this as 1 by 2 sigma square into exponential of x square. Now when you do this for multiple random variables, what happens? You just have e power 1 by 2 sigma square power n, and you have into e power
No,
some.
e power m plus n only, e power m into e power
Oh,
n.
sorry, here, yeah. And you can still break down this equation into two parts. Your g t of sigma stays, which is your 1 by sigma root 2 pi. So this whole part is 1. This part is still 1. So here xi is your sufficient estimate.
No, there is a problem. The e power mn, we cannot write e power m into e power n. E power m plus n, we can write e power m into e power n.
That's right. E power m.
But e power mn,
Yes. That's,
okay, yeah, there is a problem, I think.
okay. Yeah, I understood.
How to separate that sigma square, that variance, that parameter? If we separate, we can write like that, then we can say that it is a sufficient. That
Right.
is that variable, we call it as sufficient, no?
Yes.
That
Yeah,
is,
yeah,
yeah.
I got it. Hmm. Yeah, just have to check this. Uh, Yeah, I'll just get back to you. Yeah, check this. I'm not sure. It should be splittable, but how do you? Yeah, I'll just check this and get back. Okay. Yeah, let's just look at the rest. Okay, so in case of Bernoulli, we had this. So you could just write this as sigma theta sigma xi and into 1 minus theta power 1 minus x plus 1 minus x plus and so on. So this basically will be 1 minus theta into n power 1, n into 1 minus xi. So you can write this as theta summation xi into 1 minus theta power n into 1 minus theta minus summation of xi. So even here, the summation xi is your sufficient estimate. Yeah, this was much simpler than the previous one. Yeah, I'll just get back. Let's see how this is done. But yeah, this answers question number 5. And question number 6, you have a Poisson distribution with parameter theta. So Poisson, if you remember, it is lambda power x e power minus lambda by x factorial. So here lambda is theta. Theta power x e power minus theta by. So we can write theta power summation xi into e power minus theta divided by, here factorial, it has to be a product of your factorial xi and I is equal to 1. So, but we need to know what is the estimator of theta. So we have theta power summation of xi. So here summation xi is your sufficient estimator. Sufficient estimator of theta. Okay, this was fine. The next one is an exponential distribution. So here we have theta into x power theta minus 1. So this can be written as theta power n, and you'll have x1 theta minus 1 into x2 theta minus 2 into x3 theta minus 1 and xn theta minus 1. You'll have it like this. So it's basically a product of all your x's. So theta power n into product of I to 1 to n xi power theta minus 1. So here the product is your sufficient estimator. Yep. So previously all we just saw summation of x. So this was the sufficient estimator, but here it's the product. If you write summation here, it's the wrong answer because there's no summation.
Maybe we can say that exponential also, ma'am. We were just if you get instead of x, what is that product of xi? You are telling estimator, sufficient estimator. So instead of x, there we are having summation xi. So summation xi is the sufficient estimator for that
Yes.
random sample of the same concept, ma'am. Is it?
Yes. Yeah, same concept.
Okay.
So here we need to calculate method of moments. So we have x1, x2, x3, a random sample from a population with Poisson distribution with parameter lambda. So the method, you have to find lambda method of moment. So here, to find the method of moments estimator for lambda for a Poisson, we just equate your first sample moment, which is like m1, to the first population moment, which is mu1. So the first sample moment, this is your sample mean. And this is your population mean. So sample mean is given by x bar, the average of these observed values, and the population mean is equal to mu. So in case of Poisson distribution, your population mean would be lambda. So you have to equate this to lambda. But when you have multiple such values, what will this become? No, wait, I have new. You have, so when you take, so what this actually means, summation of xi divided by n is equal to lambda. So yeah, this is your answer. Lambda is equal to 1 by n summation of xi. So this is your lambda method of moment estimate. So you just equate your sample mean to the population mean. If you do that, you have to solve it such that you have your unknown parameter on one side of the equation, and the rest goes to the other side. So this is the answer. Is that clear? Okay. I'll just move on. So here we have a similar random sample, but this follows a binomial distribution. It has parameters. So like usually we say we have binomial distribution n comma p. But here this p is your parameter that you need to estimate. So you have n comma theta. And here you need to find maximum likelihood estimator. So if you remember, for maximum likelihood estimator, you have to do double differentiation. You have to do d by dx, then d square by dx. You have to do all that. But yeah, so basically you just have to find this, the likelihood estimate of the whatever value. Okay, let's do it step by step. So to find maximum likelihood estimate, so to make it simpler, let's just take a log on both sides. So binomial estimate is basically it's given by like n choose x into x power, am I doing it right? Yeah, x power theta. So you have x power p into 1 minus x power 1 minus theta. So here if you take a ln on both sides, so yeah, when I say for maximum likelihood, you do differentiation and then you do double differentiation. You could either directly do it on this, or you could take a ln of your function, ln of f of x, and then do differentiation. So this is just to simplify your differentiation. Doing a ln is just to simplify. Nothing is going to change, but it's just like easier. You have easier formulas for that. So now what happens is it becomes ln of n choose x. So when you take ln, this all the multiplication becomes plus. Have I written it the wrong way? Yeah, I think I would wait. So this is supposed to be n choose x, p power x, right? So it's p power x, 1 minus p power 1 minus x, n choose x. So yeah, I wrote it. It's supposed to be theta power x, 1 minus theta power 1 minus x. So now you take a ln. So it becomes this plus whatever is in the power, it comes front. So it becomes x into ln of theta plus, this is actually n minus, I'm confusing between Bernoulli and binomial. This is binomial. Okay, so binomial, this is your formula. It's n minus x. Yeah, just be very careful about these. Bernoulli is p power x into 1 minus p into 1 minus. Yeah, you forget about that. So this is your binomial distribution. You have n minus x here. So when you take a ln here, what happens? It becomes n minus x into ln of 1 minus theta. Now you differentiate. Mm. So wait, I'll just take a new slide. So here on the right hand side, you're trying to calculate likelihood of theta given x is equal to all these things that we did. So yeah, now we have ln of L theta by x is equal to ln of n choose x plus x ln theta plus n minus x ln 1 minus theta. So when you differentiate both sides. So you'll have d of ln L given x is equal to, this part is 0, and so when you differentiate this, it just becomes x stays as such. Ln theta is 1 by theta, so it becomes x by theta. And when you have something like n minus x, like 1 minus theta, you have a minus here, so it becomes minus n minus x stays as such, and this goes to the denominator, 1 minus theta. So this part, so you just equate this to 0. And so solving this, what happens? X by theta is equal to n minus x by 1 minus theta. Now if you solve this, you should get something like theta is equal to x by n. If you solve this, you'll get theta is equal to x by n. So yeah, when you have multiple random variables, what is this? This is basically 1 by n summation of xi. So this is your maximum likelihood estimate for theta. Yeah, this is the answer to the question. So whatever it is, whatever the maximum likelihood you need to do, you need to do differentiation. And you need to solve for the unknown parameter. Okay. Now let's move on to the next question. So this is method of moments estimator. So here we have this random samples from a population with a PDF with parameters theta. We have this kind of a distribution. So we have f of x. So earlier, if you remember, e of expectation of x here would be 1 by theta for this kind of an exponential distribution. Now, what do you need to do? Method of moments, you need to equate sample mean to population mean. So sample mean is x bar as usual. So x bar is basically 1 by this xi. And we have these two. So you need to equate these two. So what do you have? 1 by theta is equal to 1 by n xi. So now you need to find theta from this equation. So you just rearrange it. Theta is equal to n by summation xi. So yeah, this is your answer. And this is basically your answer. Just simple. Yeah. Sample mean, population mean. So this is always a sample mean. When you have random samples, this is always a sample mean. And your population mean would be your expectation of this function, which is 1 by theta. Equate both, find theta. That's it. Okay. Okay. So let's move on to the next question. So here a teacher uses a random sample of 150 students. So N is 150. College with a large number of students and uses a mean of observations to estimate the average quantitative aptitude. It is assumed that from the past experience, sigma is equal to 6.2 for such data. Okay, for such data, what wait. For such data, what can be said with probability 0.99 about the maximum error of estimate? So yeah, we know we had this error term z alpha by 2 sigma by root n. You just need to substitute all these values here. So here you need to find the probability, like the probability 1 by alpha. The area is 0.99. So alpha is equal to 1 minus 0.99. So alpha is equal to 0.005. We have this. So now, oh, sorry, wait. This is alpha by 2. Alpha is just 0.01. So alpha by 2 is 0.005. So now we need to calculate z of alpha by 2. So how do we do that? Normal distribution table. Yeah, we have a normal distribution table. It's a standard normal distribution, 0, 1. Z alpha by 2 was 0.005. 0.005. So you get this value. See, you get this value 2, 2.575. So 2.58. So Z alpha by 2 is equal to 2.58. You just substitute all that here. 2.58 into sigma is given in the question 6.2 divided by n is also given root of 150. So if you solve this, you'll get 2.58 into 6.2. Just give me a minute. 2.58 into 6.2, 15.99. So basically, just write 16 divided by square root of 150 is 12.25. So if you do this, you will get 1.305. Yeah, so 1.3 is the answer. So this is your error. Maximum error of your estimate is this. Okay. Now,
Ma'am, it is more than or less than
just a minute.
in the previous question.
Okay. The
In the
maximum
11th
will be
question,
less. Okay. Less than.
the maximum error of estimate will be less than.
So this is your maximum error. So any error that you get, it should be less than this.
Okay, it should be less than.
Yes. That, yep. So yeah, whatever error you get, the maximum error that you get should always be less than. Yeah.
Okay, so answer B.
Oh yes. Okay, yeah, I forgot
Okay,
to look at
thank
the
you.
okay. Yeah. Option B is
Okay,
your
thank you.
okay. Then now next question. Suppose a signal having value mu transmitted from a city value received is assumed to be normally distributed with mu and variance 36. So basically your sigma square is equal to 36. So sigma is equal to 6. Distributed with mean is 0. To reduce error, suppose the same value is sent 9 times. So n is 9. if the successive values received, so this is your x1, x2, x3. So these are your values. So you need to find two-sided 95% confidence interval. So for 95%, that means alpha 1 minus alpha is equal to 0.95. Alpha is equal to 0.05. So because it's a two-sided, you'll have alpha by 2 and alpha by 2. So alpha by 2 is equal to 0.025. Okay, we have these. So if you remember, now what is the case of this? Sigma square is known. Sigma square is known. And mu is to be estimated. Is to be estimated. So in that case, you need to apply x bar plus or minus z alpha by 2 sigma by root n. So you have to apply this to get your answer. Okay, let us do this. So x bar, you can calculate from this, average of all this. So 5 plus 8.5 plus 12 plus whatever divided by 1, 2, 3, 4, 5, 6 is by 9. So you can do this with R. You can just do mean. You can define a vector x is equal to C of all of these values. So mean of x, you'll get a value. I think you should get 9. X bar is equal to 9. You'll get this. So you just substitute those here. So 9 plus or minus. What is Z alpha by 2? 0.025. 0.025. 1.96. So Z alpha by 2 is equal to 1.96. You substitute that here, 1.96 into sigma is 6. What happened? Oops. I don't know what happened. Just went off. Oh, it's back. Okay. Divided by root n. So n is 9. Root n is root 9 is equal to 3. 3 2s are 6. 2 into 1.96. 9 plus or minus 2 into 1.96 is 3.92. So your lower limit will be 9 minus 3.92, which is 5.08, and 9 plus 3.92 is 12.92. So this is your confidence interval. Okay, you just need to remember the right formula. Everything else will be straightforward. And next, we have the same thing, but here variance is unknown. Unknown variance. Variance is unknown. Mu is to be estimated. To be estimated. But you can calculate sample variance from this x that is given. So yeah, we have n is equal to 9. Variance can be, you can just do variance of x within R. You do this and you'll get 9.5. So from this you can calculate S is equal to 3.08. So for this, what formula should you apply? This is also like a two-tailed. So here you should do x plus or minus. Here you use T alpha by 2 n minus 1 degrees of freedom. So in our case, we'll have 9 minus 1, 8 degrees of freedom. Here also alpha by 2 is 0.05. T 0.025, comma 8. What am I doing? Wait, let me first complete the formula. So it has to be x plus or minus T alpha by 2, comma n minus 1 into S by root n. Okay, wait. So we can write this as x bar plus or minus t of 0.025, comma 8. S is 3.08 divided by root 9, which is 3. So now let's find this value. So x bar also you can find mean of x with r. If you do that, you'll get 9. We already saw that in the previous question. So 9 plus or minus. We just need t of 0.025, comma 8. So how you do that? You can use, so this was normal distribution calculator. Similarly, you have students t distribution calculator. Same website, you have this. What have I done?
Ma'am, please provide the link of this table.
Hmm. Okay. Yeah, I'll put it in the chat box. Just let me know if you can access it. This is your
Yes, ma'am.
normal distribution. You should already have it. Oh, no.
And ma'am, chi-square table also.
I have it here. Chi-square.
Yes, this one.
Yes, I've put everything in the chat box. So yeah, now we need to go to T distribution table. So this is V here. So this is basically a degrees of freedom, n minus 1. So n minus 1 was 8. Write that here. Here we were interested in 0.025. I'm getting the wrong thing. 0. So you're getting 2.306. So here, yeah, 2.306. 2. I don't know why this is happening. So 2.30, no, yeah, so 2.3 into 3.08 divided by 3. So if you solve for this, you will get 9 plus 3, you'll have 9 plus or minus 2.36. So the interval will be 6.63, comma 11.4. This is your confidence interval. Yeah. Again, remembering this formula is the key. Okay. The final question. An automatic filling machine is used to fill bottles with soft drinks. A random sample of 20 bottles, so n is equal to 20, results in a sample variance. Sample variance is 0.0153. If the variance of fill volume is too large, an unacceptable proportion of bottles will be underfilled or overfilled. So we will assume that the fill volume is approximately normal distributed. 95% upper confidence bound for variance is, so 95% upper confidence bound. So what does that mean? You need to calculate this point, infinity. So what is this point? This is your 1 minus alpha, which is 0.95. Alpha is equal to 0.05. Okay, now what do we have? Mu is unknown. Sigma square is to be estimated. So in that case, what is the formula that you use? And we need upper confidence bound. So you just do n minus 1 s square by chi-square 1 minus alpha, comma, n minus 1. Let me just make sure I'm writing the correct formula. Is
Yes, ma'am.
it right?
Yes, ma'am.
Okay. We have this. So n minus 1 is 20 minus 1 is 19 into 0.0153 divided by, now we need to calculate this. So chi-square 0.95, comma, n minus 1 is 19. So remember, the curve needs to look like this, upper confidence bound. Now what do? We go to this. So degrees of freedom was 19. Yeah, it's greater than 0.95. So you get 10. 10. So you see the curve looks like this. This value to infinity. So this value is 10.117. 10.117. So if you solve for this, you will get 0.0287. So your sigma square should be less than 0.0287. That's your answer. Yep, so straightforward. Yeah, you just need to be careful about this. If you put x less than x and you write 0.95, you'll get the wrong value. You won't get it. Yeah, it won't work. Yeah. So you just need to like draw the curve manually and you'll know. Why is it not working? Something's wrong with my internet. Okay, anyway. Yeah. So this was the answer to that.
We have to put for greater than x value
Sorry? Yes, yes.
uh, uh, in the table.
Yeah, because here it's tending to infinity. So you're interested in the value greater than x, right? X is here.
Okay.
You're interested in the value greater than x. And it's 1 minus alpha.
Excuse me, ma'am.
Okay.
Yes.
Ma'am, how do we know that the variance would be less than this value?
It has to be. That is a desired thing. Oh, sorry, this is not variance. This is the confidence bound. This is the value. This is the upper confidence bound for to estimate the variance. Yeah. I don't know why I wrote this. So this is just the upper confidence bound, the value here. It has to be like 0. It's not less than.
Ma'am, this is the
Equal
critical
to.
value. So now, like there's a question in our assignment. It is
Okay.
a similar one. So over there, it is a sigma square, basically variance.
Mm-hmm.
I was able to find out the critical value, but I was not able to tell that variance would be greater than that value or would be less than that value. So how can we find that thing?
Mm-hmm. Okay. So I would think it should be less than or equal to this value 287. So this is basically you're actually estimating the variance here. Yeah, so sigma square is to be estimated. Okay. Yeah, so basically with this formula, you're estimating sigma square and it has to be less than this value, anything. I don't know why, like how do I explain that? So this is the upper limit of the variance that you expect. You can't go beyond that. If you go beyond this value, it will fall outside of this confidence interval. So if your sigma square has to fall within the 95% confidence interval, it has to be less than 0.028. If it's greater than this, it will be outside your confidence interval, which is this area. Does it make sense?
And that is absolutely all right, but how do we know that?
Ma'am,
Yeah,
the value should be less than or greater than sigma value should be less than.
sigma value should be less.
So sigma value should be less than.
Yes. So
Okay.
yeah, that's what I was trying to rephrase. So with this formula, you are estimating your sigma square, some value you are estimating. So what does this value mean? So this value basically lies within your 95% confidence interval. It lies here. So it has to be less than that, or it can be equal to that as well. If it lies above that value, it means that it doesn't lie. It lies outside the interval. So yeah, your sigma square always has to be less than equal to that estimated value.
Less than or and equals to.
Yes.
Okay.
Yep. That's it. All right. Oh yeah, one more thing. So we just have one more session left. I don't know. Like I haven't got the slot for an additional 1 hour's class. So okay, if we have that extra session of 1 hour, so which that is basically just like a revision session. So what would you want me to revise? So that 1 hour, what would you like me to do?
Ma'am, for coming session,
Yeah, so next Tuesday we'll have week 12 revision. And then I think
okay.
Wednesday I'll have an extra 1 hour. Or I might not. I haven't got the confirmation yet. But yeah, I am supposed to take another extra hour. So when is your exam?
Ma'am, till not we have not provided the
28th of
admit card.
April.
Okay,
The probable date is 19 or maybe 26.
okay. Then yeah, we will be having a 1 hour session extra. Apart from your week 12 live session, we'll have one extra 1 hour session. So that's
Ma'am, in last assignment question, 10th assignment question, the question number,
normal distribution. Is that?
yes,
Yeah,
last
yeah, we can discuss that. Question number,
last two questions.
what is it? Week 10, right? Week 10, last two questions. Okay, yeah, do that. Yeah. Apart from that, I can just try to like compile all the important formula and just quickly
Okay.
brush up.
Ma'am, that will be beneficial for our examination point of view. Please.
Okay. All right.
Yes, ma'am. What you can do is that you can,
Mm-hmm.
of all the distributions, you can basically you can create a slide
Okay.
in
Right.
which there are all the PMF of all the distributions,
Mm-hmm.
mean and variances,
Yes.
some questions.
Okay.
And ma'am, the
All the weeks, ma'am.
tables are provided in the examination.
Yeah, your table should be provided in the exam. Or
Oh,
you could like you might be able to access the site.
okay.
Yeah, I'll just ask that as well. Will tables be provided? Okay. Yeah.
And ma'am, in third assignment, I forget that question. It's something in assignment third. I have to ask. I will ask that. on
Let me
live
just,
session.
yeah, I can open that for you. Stop sharing this screen.
Do we have to remember the R commands?
Yes. But I don't think you'll work on R. Let me ask that as well. Like, I don't think you'll have access to R Studio.
No, ma'am, we won't be having the access, but is it possible that they give the 4 options
Yeah,
and
that is
from that
possible.
to
Yes, that is possible.
choose which is the correct syntax?
Yes, yeah, that you might need to know. We'll get some questions. Sharing screen. Week 3. Yeah, which was the question?
Ma'am, I think there was some concept. I just forget that. I will find it out and let you know that.
Yeah, you can let me know next Tuesday.
Ma'am, week 3, question 5 as well.
Question 5.
Yes, ma'am.
Okay. Week 3, question 5. Yep. I'll try to solve these. Anything else? Yeah, if there's nothing else, we can meet next week. Next Tuesday. Oh, somebody CLT related problems. Central limit theorem. Okay. All right.
Ma'am, shabby chef inequalities related to that.
What is it?
Shabby chef inequalities.
Okay. All right.
And ma'am, in multiplication theorem of probability, there is one question like an ordinary deck of 52 cards is randomly divided into
Hmm.
4 piles of 13 cards each.
Yeah, I remember
Compute the
that.
probability.
Okay.
I I just want to
Yeah, I
I
remember
just
that
want
question.
its explanation.
Yeah, I can revise that.
Okay, thank you, ma'am.
All right. See you next week then. I'll upload the recording. Like you'll have it tomorrow morning. I can upload the
Thank you.
slides now. Yeah. All right. Good night.
Thank you for the session.
See you next week.